to a couple of cases. We will do a block theorem, and also we will consider a general procedure for analyzing normal modes of molecular crystal vibrations. But before we do that, I would like to recapitulate what we did last time with the product representations, because it is one of the important application of group theory, and it's also related to angular momentum theory. So let me share a whiteboard here. So we say that if we have an irreducible representation T alpha and corresponding basis functions psi alpha I, and another irreducible representation, let's call it beta, with the corresponding basis function, call it phi beta, like so. Then the product functions by j beta, and these product functions then transforms under the symmetry equation according to the direct product representation. So if we apply symmetry operation on this object, then we get sum over I prime j prime of psi prime of psi beta j prime, and the matrix will be the direct product matrix. Prime, sorry, I prime, yes, so j prime like this. So I thought I made a mistake here, sorry. So this should be so then it should be j prime. I think I made a mistake here. It should be ij prime ij like this. Yes, so it forms a matrix multiplication here. Yeah. So this product representation, so I'm just repeating what we did last time, can be decomposed. So we just write it as like a shorthand to its irreducible representation like this. So this is a shorthand. So the meaning of this is that we have a matrix T alpha cross beta, and we have the Clebsch-Gordon coefficient, which brought this scrambled matrix T alpha cross beta into a block form. So this is the meaning of the right-hand side. So the M gamma tells us how many gamma representations appear in the decomposition. So for example, I could have T alpha twice, and then T beta, and so on. Yes, number of times. So this is actually what we do when we combine two angular momenta. So clear that. So in angular momentum theory, we have angular momentum states included by J and M, and we have combined it with another combine it with another state like that. So let's call this a state M2 like this, because J1 and J2 are given. So we have then the rotation operators. So as you know, the angular momentum operators are generators of rotation. So usually we call it D here like that. So if I just look at one angular momentum state that we know is given by sum over prime, same J, but different M. Like this. So you know that if you rotate an angular momentum state, then it's a linear combination of the other M components. And this is the irreducible representation of the rotation group. Yeah. It's irreducible because it's not possible to convert this into a block form. Now you can also look at the effect of the rotation on this state here, the compound state. And we then have M1 prime, M2 prime. And these states now transform according to the direct product representation. So this will be J1 times J2, M1 prime, M2 prime, M1, M2. So this precisely has the same form as the general case that we consider. So it's just that now it is specialized to angular momentum states. So this direct product representation of the rotation can also be decomposed. So if we write G1 cross G2 like this can then be decomposed into this well-known formula that you have the capital J to indicate that's the total angular momentum. So that goes from J1 minus J2 to J1 plus J2. So that's, so that is J, like that. Schematically, we can write it like this. So it is exactly the same thing that we have a matrix J1 cross J2, and then we have the Clebsch-Gordan coefficients that transform this into a block diagonal. So now this will be the J1 plus J2 block like this, and then we have the J1 plus J2 minus 1, it's also a block. I need a bit more space, but you can see that at the end we have the J1 minus J2 like this. So let me move up. Let's skip it. Sorry, so let me repeat. It's very easy to touch wrong button. This iPad. So what I want to say is that we can decompose this into the reducible representation like this. J1 minus G2 like that. So this is block like this. 0, 0. So if we look at the vector, and we can see very clearly that because of this block form, then this set of vectors would correspond to the J1 plus J2, and the next one would be J1 plus J2 minus 1, and so on. So the special thing about the rotation symmetry is that the decomposition has only one irreducible representation each. So I just erased it, the previous one, but if we write it again, we'll see this. So J1 plus J2, and this becomes J. So this Mj here, Mj is equal to 1. So there's only one irreducible representation for each of the capital J. But otherwise, the algebra or the mathematics is the same as decomposing the product representations into its irreducible representation. And also that we can understand this Wigner-Eckart theorem in a simple way. So let me go back. Where is that? So this is the Wigner-Eckart theorem. So this can be understood that if we recognize that this quantity here, or this object, or the state, transforms according to the direct product representation T alpha cross beta. And then one can decompose this product representation into its reducible components, M gamma, T gamma, like what we just showed. Then it becomes obvious that this state here, psi gamma, or this one here, rather, must belong to one of these irreducible representations, because otherwise it's 0. So it's a rather useful theorem. I mean, imagine that you try to calculate the matrix elements of some operators without taking into account the symmetry, and then after a lot of effort to compute the matrix elements, you find that it's 0, or maybe if you use computer, it would be like 10 to the minus 16 or something. But if you analyze the symmetry, then we can maybe tell already from the beginning that it should be 0. We don't even need to calculate it. So then so that's one useful use of the symmetry. Okay, so now we have also the symmetry breaking. So that's basically, I think we talked about it before. So then we have a bunch of degenerate states. Then if we lower the symmetry, then it generally will split to, again, several states. And we can tell how these split states transform according to the lower groups. And we also talked about the partial diagonalization of an operator, in particular the Hamiltonian. So if we look at the Hamiltonian, it is just a special case of the Wigner-Eckart theorem. Let me repeat this because it's important. So this is some constant. Let me call it A instead of C, so it's not a Clebsch-Coulton. Delta alpha beta delta ij. So the Hamiltonian, of course, we are assuming that the Hamiltonian has a symmetry has a certain symmetry, is invariant under the symmetry transformations. So that this implies that the Hamiltonian transforms according to the identity representation, because it just goes back to itself when we make this similarity transformation. So the Hamiltonian then, if it has a certain symmetry, it follows the identity representation, or it belongs to the identity representation. Then if we consider this quantity here, well, because H transforms according to the identity representation, then this object here transform according to beta representation. So then that's why we get this result immediately. Okay, so that's a recapitulation of what we did. So now I want to consider a real example here. So a nice example is a block theorem. I don't know if you have done the solid state physics, but I should repeat this then. A block theorem is a statement about the eigenstates of a Hamiltonian in which the potential is periodic. So you have a potential which is periodic, like in the lattice, in a crystal. Then the eigenstates of the Hamiltonian fulfills a certain properties, and this is called the block theorem. So what we have is a lattice. Let me just do this in 2 dimensions because it's going to be difficult to do this in 3 dimensions. So we have a lattice like this, and I have a vector. Let me vector. This is called the lattice vectors. Call it A1 and A2. So these dots here are just the atoms in the crystal. Let's just do one atom, one particular species of atom. And in general, we can have many atoms, but let's just do it for one atom. Then we have a third vector, A3, which will be in the third dimension. It's not necessarily perpendicular to the plane, can be in any directions, but it has a Z component. Yeah. So then we have translational symmetry, because by definition, this potential is invariant under translation. So we can construct a vector, call it T for translation. Like so. So I can form a linear combination of these lattice vectors, A1, A2, and A3. So N1, N2, and N3 are integers, of course. So then the potential, if I translate it by T, will be just equal to R. That's what we mean by periodic. These are for all possible integers, including minus. So it's a minus negative and positive integers. So these lattice vectors, it's a bunch of lattice vectors, T, will then generate the lattice points. Yeah? So the important point about translation is that they commute. It's kind of obvious, yes? If you translate with a certain vector and then another one, then it doesn't matter the order. Yes? So you can translate in both ways. So I mean that if you do a translation like this, let's say this is T1 and then T2, well, that's the same as going T2 and then go T1. Yes? So they commute. They commute. So then this translational group, and this is the elements of the translation groups, the T, then can be written as a direct product. So this is important, direct product. And we have a T, T1 cross T2 cross T3. Yes, where T1 means just a bunch of translation vectors along A1, T2 along A2, and so on. So, so we recall that if we have groups with elements commuting with each other, then they are abelian. The group is abelian. And we can also think of it as a direct product group because the elements commute. The elements of T1, T2, and T3 commute. So we can form a direct product group. Now we have an additional condition. So this is usually called periodic boundary condition. So we impose periodic boundary condition. It's called, I think, the Born-von Karman boundary condition. Von Karman boundary conditions. It's basically say that if I translate by an amount n1 u1 on the some wave function, then this is, by definition, this is equal to r plus n1 a1 like this, and this is equal to the function itself. So there is a periodic boundary condition. This is a definition. This is also true for the other translation vectors for A2 and A3. Yeah. So now, because of this periodic boundary condition, then the translation group becomes a cyclic group. It's because it repeats itself. And we have figured out the irreducible representations of this cyclic group. So we did that before, very beginning. So the irreducible representations of the cyclic group is given by this exponential by k1 divided by n1. So n1 can be chosen to be very, very large. In fact, in theory, it should be taken to infinity. But let's just keep it finite and large here. So k1 is just integers. So 1, 2, 2, and 1. So, and we have the same for the other two, groups, the other two subgroups. So usually when we deal with a lattice, we work in the what's called a reciprocal space. Reciprocal space. So this is a bit like in the Fourier transform. You work in the momentum space. So you define a vector. It's reciprocal lattice vectors. It's called. It's defined like this: A2 cross A3 divided by the volume dot. Should be a bracket there, like that. So it's the definition of the reciprocal lattice vectors. Reciprocal lattice vector. So there's another one, another two, of course, G2 and G3. Yes, very similar. You can see this in the notes. But it has the property, I think you can easily check this, that if I take dot product between Gi and Ej, this is equal to 2 pi delta Ij because of these constructions. Yeah. So the direct product representations. So we recall that if we have a direct product group, then the irreducible representation of the direct product group is simply given by the product of the irreducible representations of each group. Yeah. So then the irreducible representation of the full group, the full translational group, then it's given by this. It's labeled by k, by this k vector, and by some element. So T here is the element of the group, or an element of the group, I should say. So then it's equal to k dot T, like this. So now this K here, this is where the reciprocal lattice comes in, is given by K1 divided by N1 times G1 plus K2, G2, K3, 3, G3. Okay. So now we get the block theorem because we have one-dimensional irreducible representations. So it follows immediately that we apply translation is an operator on the eigenstates of the Hamiltonian. So we recall that the eigenstates of the Hamiltonian can be used as a basis for the symmetry group. So here we have a one-dimensional representation. So we just have one state. Call this one here. These are the eigenstates of the Hamiltonians. So eigenstate of H, which has the periodic potential. So this by definition is equal to psi k plus t, because we just translate the coordinate. Then we see from the general form, let me use a little space here. We recall in general we have a group element acting on the basis. This becomes psi j by j alpha, and then we have the representation T alpha. So now this representation is one-dimensional. It's just this number here. So then this is equal to psi k r to the I k dot t, like this. This is the block theorem. So it's the block theorem. So it tells us that if we translate the coordinate by some translation t, there is a vector here, then it is exactly the same eigenstate, but multiplied by a phase factor. So actually you can also write this as plane waves, which is the same here, times some periodic function. You can show that easily. So this is periodic. This is not periodic. Yes, this the eigenstate is not periodic. As you can see that if you translate by t, it acquires a phase factor. It's a block theorem. So actually, block theorem is just is equivalent to what's called the Floquet theorem. So Floquet actually worked this out already in 1883. So block theorem is in 1928. Just a little bit of history here. Well, there is also Floquet. I think his name is Gaston Floquet. He's a mathematician, and he has exactly the same theorem, but I don't know why this is done, because I think probably Bloch didn't know about this Floquet theorem. It's exactly the same theorem, except that he did not consider lattice, but more general differential equations with a certain periodicity in the potential. Okay, so that is one example. So we can think of Bloch theorem now as a consequence of translational symmetry. So this phase factor here is just the irreducible representation of the cyclic abelian group. that's different way of looking at the block theorem. It was not how it was derived originally. So the next example I would like to consider is the it's analyzed in normal modes. So we have some molecule. So we're talking about the molecule here with we have some atoms. So we have then some potential. So we have some Hamiltonian with a kinetic energy. Energy plus some potential energy. So it's going to be here. So the V then we can expand it in terms of the displacement of the atoms. So we have n atoms, let's say. And we imagine that the molecule is in equilibrium. And now we displace each atom a little bit from the equilibrium position. So we can then make a Taylor expansion of the potential. So we have the value of the potential in the equilibrium position. So this is equilibrium plus first order Qi like this. So Qi here is the displacement plus second order two, three. Okay, like I have in the notes, and so on. This is a Taylor expansion. So Qi is the displacement of atom I. So this is the displacement of atom I. Yeah. So if you look at then at the Hamiltonian, then we have some the kinetic energy. I call it Mi. So actually we have not done quantum mechanics here, it's just the classical mechanics. So we have Qi squared, Q dot here, so that's the velocity. Q is our coordinates. Then we have, so now V0 is just a constant, so it's not interesting because that just shifts the eigenvalues or the total energy of the system. So we can drop that. And this thing is now calculated, all of these derivatives are calculated at equilibrium. It's calculated at equilibrium. But at equilibrium, the derivative of the potential with respect to the displacement is 0. So then we are just left with the second order. So this is usually called the harmonic approximations because we only keep the quadratic term. So we neglect higher order terms. Yes, this is harmonic approximations. Okay. So we can rewrite this in terms of the new variables to make it look nicer. You can define it like this. I can call Tij equal to Bij divided by square root of mj. Then if we do this, if we use these variables, and Hamiltonian become simpler, or looks nicer at least. It's not simpler. So looks cleaner. Dij alpha I alpha j, like that. Yeah. So this matrix here is usually called the dynamical matrix. So this is like what you have when you do phonons in solids. You have dynamical matrix. That's exactly what this quantity is about. So now we want to solve this problem using normal modes. So what do we do here? So we introduce kind of 3n, three-dimensional space. It's kind of abstract space. So we have n atoms, q1, q2, and q3n. So 3n because we have three Cartesian coordinates for each atom. So then the total there will be 3n coordinates. And we write this like q vector, big vector, linear combination of some bases. Yeah. So it's just a way of writing this collection of coordinates representing the movement of the atoms. Yeah. So we can define an operator acting on particular of these basis vectors. Like before we have dij like this. And so dij is then just the matrix elements of some operator d. And so that the potential can be written as the product between some in D, which is the dynamical matrix vector. So that's equal to 1/2. So I'm just using this expansion here. So we get alpha I, alpha j, and then the dot product between the bases. So then this equal to what we had before. Okay, like this. So now we to diagonalize this Hamiltonian and look at the normal modes. So we see that we can do it in this way. So we introduce a new coordinate, call it UK, not coordinate, but basis vectors, which we define to be linear combinations of the original basis. So what do I call it? Aij there. Oops. Like that. So now we can write an arbitrary vector q as a sum over IEI alpha I, like we had here. And then this can also be written in terms of the new basis, in terms of the UK basis, and called the coefficient UK, like that. So then this is equal to sum over KI, EI, AIK, QK. That's I'm using this expression here. So then we recognize that this alpha I is equal to just the sum over K of AIK QK, like that. So far we have not said anything about this new basis. We just say that it's some linear combinations of the original basis. But if we choose this UK, this new basis to be eigenvectors of D, so this, so we choose UK to be eigenvectors of D. So we have D UK is equal to some eigenvalue K, call it omega K. Then the Hamiltonian has a diagonal form. So this is the usual trick of transforming Hamiltonian to a diagonal form. So basically we have kind of diagonalized Hamiltonian, and of course then the form becomes diagonal. It's nothing funny about that. So let me look at the time. Okay, so we have 1 minute and we can finish part of this. Okay, so far we are just talking about the system in a classical way. We have kinetic energy and potential energy. So we have not done quantum mechanics, and we have not used group theory or anything like that. It's just a general consideration of molecular vibrations. So this is what we normally do. We have this Hamiltonian, and then we want to quantize this. So what we do is then we replace this thing by an operator. So that becomes derivatives like this, second derivatives. So we recognize as the momentum operator. And then we get harmonic oscillator Hamiltonian. These are just quadratic in their displacement. So we know the solution. So then we have the harmonic oscillators. Call it NK like this. So that is some constant times the Fermi polynomials. Okay. Times let me see. So these are just some details about the solutions. It's not so important actually for our purpose. But let me just write this down like that. And this energy, the energy for each mode is given by the usual harmonic oscillator energy time omega k. Yes, you recognize this. We now have different case. Instead of just one harmonic oscillators, we have many. So the k goes from 1 to n. It's n is the number of molecules in the crystal, in the molecule. Okay, so this is we have so far. So now we want to apply group theory. So we know that let's say that the molecules has a certain symmetry. So we have a set of symmetry operators. G. So G here usually is just a rotation. If we have a molecule, then by definition, these operator commutes with a Hamiltonian. So that actually implies also that the symmetry operators commutes with its dynamical matrix. This dynamical operator 0. So this implies also that the eigenvectors of the D matrix, of the dynamical matrix, can be used to spaces for the irreducible representation of the group. That's a general result that we have before. The degenerate, I should say degenerate in general, degenerate eigenvectors of D can be used as basis for irreducible representations of the group. Okay, there's quite a bit to do here, so maybe I can stop here for a break. Yeah, maybe that's better. We need quite another 10 minutes or so. Okay, so maybe we continue then at 11:15, say. So if you have questions, you can, of course, ask. If you don't have questions now, we can meet again at 11:15. And if you have questions later, you can always send me emails. Okay, I hope everybody see if yeah. So I hope everybody is back, and we can continue with this vibrational modes. So you want to analyze the vibrational modes of molecules according to the irreducible representations of the group. So we say that by definition, the symmetry operators of the molecule, of the symmetry group of the molecules, should commute with a dynamical matrix or the dynamic operator. Now we need to introduce basis functions or basis vectors. So for this problem, we have the Cartesian coordinates. So to each atom, we have 3 Cartesian coordinates. This, and the I is X, Y, and Z, and the R here labels atom. Labels the atom. So these are our basis functions, or basis vectors. So we have Cartesian coordinates X, Y, Z attached to each atom, which we label by R. And so I should not confuse this R with rotation. So this R is just a label for the atom. So this means that there will be 3 times n basis vectors, because each atom has 3 Cartesian components independent. So then there are 3n basis vectors. So this implies that the representation for the symmetry group is a 3n by 3n matrix. That's because we have 3n basis vectors. So our goal is then to decompose this representation into the irreducible representations of the group. Okay. So if we work with a character instead, the character of the 3n representations. So this is the character based on the 3n basis vectors, can then be decomposed into the various irreducible representations like this. So we will use the formula to compute these coefficients m gamma using the first orthogonality relation. So that's our goal. So if we look at the effect of the symmetry operator on one of the basis vector, so let's take EI R like that, then that will bring, this will be a linear combination of the other basis vectors in general. Or there should be an R prime here, I think. Forgot the R prime in the notes. Okay, R prime R like that, and G. So the sorry, there's no I mean mistake. There is no atom. There is no summation over the R prime here. Yes. So the point is that this operator rotates atom R, or brings atoms R, rotates atom R to atom R prime. So that's what we mean here. Yeah. So this is usually a rotation. So that rotates or move atom R to atom R prime. So now the character of the representation of the 3n representation for a given G, is then just sum over I of this thing, matrix elements of the symmetry operator in the basis, this Cartesian basis. So that can be written then as sum over I, sum over J, because I'm using this result here. So that becomes the I R E J R prime and the R prime or Ji, like that. So now there is one important point here, is that this the trace of this representation is zero if atom R is different from atom R prime. So if R or if R prime is not equal to R, then this doesn't contribute to the trace. It's because this thing is zero. It's equal to zero if R prime is not equal to R. So then it is not difficult to compute this trace here, because we just have to look at the geometry of the molecule, and we only consider those rotations or the symmetry operations that keep certain atoms unchanged, unmoved. Yeah? So only those atoms contribute to the character. So only atoms which are not moved contribute to chi 3n. Yes, I think this is clear. So if we look at then the character, this 3n representation is then given by 3Ri T R R I I. So the R prime must be equal to R. And this is just the number of atoms unmoved by the symmetry operator, and multiply by the character of the three-dimensional representations with the Cartesian coordinates as basis. So we call it V for vector representation. So this is the vector representation with x, y. Sorry, let me remove this. So Ex, Ey, Ez. Yes. So locally, this is the representations of the group. We use the Cartesian vectors as the local basis for each atom. So we just repeat here. So we have molecules and we do a symmetry rotation. Then in order to calculate the character of the representation, the chi3n, then we only need to consider those atoms which are not moved by the rotation. So that is why we have just NR, the number of atoms which are not moved. Not move times the character of the vector representation. So the vector representation just means that there is a representation based on these Cartesian coordinates ex, y, and ez. Yeah. So it's not difficult to calculate this trace or character of the big representation. So let's illustrate this by a simple example. So we always use the D3 symmetry as our example, D3, or this is equivalent to the S3 group, the permutation group of 3 objects. So we did that already several times. Just to remind you, so we have, this is the group corresponding to equilateral triangle, like that. We have several axes, symmetry axes, D1, D2, and D3. D3 here. So we have 6 elements, and we have worked out the characters based on this basic vectors here. So if you go back to the examples we had before, we can see that the character for the unit element, which forms class by itself, is equal to 3. And for the characters corresponding to rotations about the z-axis, so C here. So you recall that we have 6 elements of E, C1, C2, and then D1, D2, D3 is equal to, what was it, 0. CD is equal to -1. So this we have worked out before, yes? So now, if we consider rotations, let's say one of these, let's look at this C rotations. Well, the C rotation obviously rotates the atoms to a different place. So this would mean that the new atom, R prime, is not going to be equal to R. It's for the C1, C2, because we rotate the molecules around the z-axis, which is perpendicular to the plane, then all the atoms will change place. So then it doesn't contribute. That's why it's called. It's just 0. Okay. For the, so we have chi3n of the C is equal to 0, and of course we have also the one corresponding to the unit elements, where we do not move anything. So that there will be 3 atoms which are not moved. So we are using this formula here. And the character of the vector representation for the unit element is just 3, because it's a unit matrix. 3 by 3 unit matrix. So then the character is 3. So we get 9 here. And then for the D diagonal rotations, what do we have here? We have just then one atom, yes, because we take, for example, D1. So we look at this. These 3 atoms are located at the vertices. So we look at D1, which is a rotation about this axis, D1. Then this atom is fixed. It does not move. So that's the only one that contributes. So it's 1, yes, times the character for the C. I think it is -1. And look it up. That's -1, like this. Okay. So I also have written this down in the notes. So now we want to decompose this representation. So that's a 3n by 3n representation. So we want to decompose that. So that's straightforward. So we just use the first orthogonality relation, gamma, like that, and compute this thing. So let's write this down. So the gamma, according to the orthogonality relation, is just given by 1 upon the number of group elements, sum over the class, because remember the character only depends on the class, not on the group elements. So group elements belong to the same class as the same character. So what we have to do is just use the orthogonality relations, the first one, like this, times chi. This will be the 3n ck, like this. So the characters of the group, so this is where the character table comes in. So that's why the character table is very important, it's essential when we want to apply group theory to real problems. We just sketch this again. So we have, I think, three reducible representations. So T1, T2, T3, and then we have 3 classes, CE, and then the 2 elements belong to class C, and 3 belonging to the class T. First one is identity representation, and the dimension is 1, 1, and 2. Like this, so we have worked this out before. It's the character table. And here we have 1, -1, -1, and 0. So if we use this table, we can easily compute the coefficient and gamma. So let's take an example. So let's take M3. So I'm looking at this table, this row here. So then according to this formula, it should be equal to 1 upon 6. So now I'm summing over the classes. So the number of element in class ECE is just 1 here. And then I have the character for that class is 2. So it's 2. This one here. And then I look up at the character that we just worked out before. So what do we have before? So we have chi 3n of C is of course 9. Of the C is equal to 0. And chi 3n CT is equal to -1. Okay, so we just use this information here. Just multiply by 9. Now we go here. So that is -1. Oh, sorry, number of elements is 2. Here is that. So 2 elements, 2 elements, and multiply by character -1. and multiply by 0. So here, 0 doesn't contribute anything, and so on. So we have 3, okay, and then multiply by 0, so that also doesn't contribute anything, and times -1. So you see that this is equal to 18, this is 0, 0, 2, 3. So that's nice because it should be an integer. If we get some funny numbers, fraction, then we know we have done something wrong. Okay, so we can do the same for the T1 and T2. So we get, we do that, look at my notes here. So 1, 1, and equal to 2. Yep. So these two representations, I think this is one-dimensional. You can see it's one-dimensional. So the third one is dimensional, and there are 3 of them. So if we count the number of states, and we see that it fits because that we have 3 times 2, so that's 6, and then we have 1 and 2, so that gives 3, and that's 9. That's what it should be. There are 9 basis functions, so we should have also 9 in total. So what does this mean? So this means that there are 3 non-degenerate modes. So this 3 non-degenerate modes because these two representations, T1 and T2, are one-dimensional. So the degeneracy is determined by the dimension of the representation. So that's important. Degeneracy is determined by the dimension of the representation. And we have 3 for the third representation, but it is a 2-dimensional representation, so it is doubly degenerate. So that means there are 3 doubly degenerate modes. 3 doubly degenerate modes. So we see that by analyzing the symmetry, we can tell how many modes we have, how many distinct modes we have, and how many are degenerate, and what is the size of the degeneracy. Of course, we do not know the frequencies of the vibrations. That we have to do some computation. That depends on the molecules, obviously. But the general feature, that is to say, in terms of the degeneracy, for example, this is just determined by the symmetry. So if I have several different molecules, but they have the same symmetry, then we know that how the vibrational modes are split into the different modes and the degeneracies of the modes. And also by classifying the vibrational modes into their irreducible representations, according to the irreducible representations, then we can make use of the Wigner-Eckart theorem. When you want to calculate matrix elements between one mode and another mode. So it's exactly the same kind of algebra that we have before, the Wigner-Eckart theorem. So we could have an operator that relates one mode and another. So we know the symmetries of the operator. We can then figure out which matrix elements are 0 or not. We cannot tell the actual magnitude because that has to be determined by actual calculations, because that depends on the potentials of the molecules. Okay, so this is one example. So one of the assignment is working out this normal modes of some real molecules. So actually, they are real problems, and you can check your results in the link that I provided in the problem. And there's a little bit of mismatch here, but we will do vibrational modes of water molecule next Wednesday. It's a concrete example, but I think you can already do part of the assignment problems.
Yeah, hey Ferdy.
Yes.
I don't remember anymore what you wrote, but I'm looking at your lecture notes, and when you wrote the Hamiltonian, shouldn't you have the omega squared? Are you missing like omega squares? Also in the dynamical matrix equation, is that omega squared?
In the dynamical matrix.
Like page 53 of your lecture notes.
Okay. It's possible that I made a mistake. You mean in the Hamiltonian?
Yeah, shouldn't that be omega squared?
Okay. That could be, yes.
And then also the dynamical matrix is du omega squared u.
Omega squared is not true. Okay, I have to check that. I cannot see this because this omega k is supposed to be the eigenvalue of the D matrix.
Okay.
So I don't see why you have omega squared.
I just remember seeing that there's usually omega squared if it's the frequency.
I see. But this is just the eigenvalues.
Okay.
Of the dynamical matrix. But I will check. I will see.
Yeah. And then I have one question about this longitudinal transverse optical splitting. Is that symmetry breaking of this? If you know phonon dispersion, then you have this LOTO splitting. Is that a symmetry?
Yeah.
Okay.
Well, those are just the modes, yes, of the phonons.
Yeah.
So the longitudinal and transverse modes.
Yeah. But I have this, the character table shows it should be threefold.
Yes, then that means, yeah. So if you break the symmetry, then you can split those vibrations, vibrational modes.
Okay.
Yeah. Any more questions before I continue with the permutation group? We have a little bit of time. We have 15 minutes to do the permutation groups. But we will do an example, a real example, next Wednesday during the exercise class. We'll take up water molecule and analyze the vibrational modes. So in principle, we can just take any molecule. So the important input is the character table. When we know the character tables, then we can figure out these modes. So the phonons are more complicated because you also have to take into account the translational group. Yes, but in principle, that is the same kind of algebra, same kind of procedure. Okay, maybe we can then continue with those permutation groups if you don't have any more questions on this part. Here. Okay. Yes, permutation groups. So this is actually math, no? But permutation groups has a lot of interesting aspects. So they are related to many physical problems. There are several important things about the permutation groups. So, for example, we have this Cayley's theorem, famous Cayley theorem. It says that any finite group of order n is isomorphic to the subgroup of the permutation group of n objects. So that's a useful theorem, because then we just work with permutation groups. We know the irreducible representations of the permutation groups and their subgroups, and basically all the finite groups. All the irreducible representation of finite groups are known by solving the permutation group problems. In physics, we know that we have permutation symmetry associated with identical fermions and bosons. And later, when you do continuous group, it is also related to the SUN groups. So we will do some Young diagrams to study the permutation group, and there are some rules about how you multiply two Young diagrams. So we will not do it here, but maybe Malin will do this thing, because she will consider the SUN groups. So this has to do with collisions of particles, for example. You have two particles belonging to two different SUN groups, and then you can analyze how the different possible splitting of the product groups. So the permutation groups have been studied a lot, so you can find books on this that specialize on some permutation groups. So we will not have time to go through all the proofs. So some of the proofs we will just state, but they are given in the notes, yeah? Except one theorem, which is not given. We'll come back to that. So if you're interested, then you can just read the notes. But we just try to go through the proofs of some of the important results only. Okay, so let's start with the definition. Yes. So we write the permutation in this way here. So this just means that we have n objects, 1, 2, 3, and so on until n. And we permute them. So 1 goes to P1, 2 goes to P2, 3 to P3, and so on. So P1, P2, P3 are just numbers. 1, 2, 3, and so on. So it just permutes the element. So this is not the only way of writing permutations. That's one way. Yes. So one important thing is that the ordering of the column. So we order this thing here, and it's not so important. So what's important is the mapping. So for example, 1 goes to P1, 2 goes to P2, and so on. So we look at an example here. 1, 2, 3. Let's say we have 3 objects. Then this is the same as this one here. So as long as we keep the mapping, 2 to 3 to P3, 2 to P2, and 1 to P1. So the ordering of the columns is not important. It's kind of clear. Then we have also the inverse. So the inverse just means that we just reverse this thing. That's the inverse. Permutations do not generally commute. So if we do P1, P2, that's not equal to P2, P1. It's not the same. They do not commute, in general at least. So, yeah, so that one way of writing a permutation. But it is also possible to write permutations using what is called a cycle notation. It is also a useful way of writing permutations. So I think we just consider an example, it will be clear what it means. So we take this as a permutation of 6 objects, just one particular permutation here. So we see that 1 goes to 5, 1 goes to 5, and then 5 goes to 2, and then 2 goes back to 1. So then I can write it as a cycle like this, 1, 5, 2. Yes, because 1 goes to 5, 5 goes to 2, and then 2 goes back to 1. So it's like a cycle. And if you look at the element 3 here, 3 goes to 6, and then 6 goes to 3, goes back to 3. So then I have the 2 cycle, 3, 6. And then finally we have just a 1 cycle. So usually the 1 cycle is omitted, but you can also write it down like this because it's kind of redundant. Yes? And so if it's just not written, it means just a 1 cycle. So important point is that when we write in a cycle like this, we have to be careful with the order. So 1, 5, 2 is equal to 5 to 1 because it's cycle, 1, 5, 2, back to 1, and so on, and 2, 1, 5. But it is not the same. There should be a bracket here. But it's not the same as 1 to 5 because that we change the order. So the ordering of the cycle is important. That's the same also clear. Now we have this famous Cayley's theorem. So I want to prove this. Okay, I have it here. No, I don't have it here. Okay, so let's do this then. Sure. So, so the idea behind the Cayley's theorem is really based on the multiplication table. So you have group G1, G2, G3, and so on. Gn is an element of the group. And I have another element here. Let's say A. So A can be one of these G1, G2, C, and so on. Then this becomes AG1, AG2, AG3, and AGN. Yes, I just multiply. But we know from the rearrangement theorem that these are just permutation of these elements. So these are the permutation of G1, G2, and so on, Gn. So then we can try to represent the element A by a permutation. So we write then A is equal to G1, G2, so on to Gn, and AG1, AG2, AGN, like this. Yeah, because this is the permutation of these elements G1, G2. And we are sure that all these elements are different because we have this rearrangement theorem. So we want now to show that if we take 2 elements and multiply them, then this representation in terms of permutations should also fulfill the multiplication rule. It's a closure relation. And before we do that, we need one thing. We need to know one thing here. So if we have G1, G2, Gn, and AG1, AG2, AGN, like that, that is equal to this element. A PG1. So I put it in a bracket to make it clear what's going on. Yes, because it's the mapping which is important, as we said before. It's the mapping from one element to another. So it doesn't matter whether it is G1 or G2 and so on. As long as the mapping is preserved, then we have the same element, the same permutation. So for example, if I look at this one here, So G1 is mapped to AG1. Well, it is somewhere here. We don't know. It could be, let's say, this one. So if BG2 is equal to G1, then we have G1 mapped to AG1. Because if, for example, yes, BG2 is equal to G1, let's say, just as an explicit example. So we can do this. I think that's clear. So now let's check. So let's say that we have two elements. We take two elements A and B, and apply that. Let's say that is equal to C. Yeah. So we just check that this multiplication is fulfilled. We replace A by the permutation. So we have that G1, G2, Gn, AG1, AG2, and I have all these things in the notes, but now I want to go through this step by step. And now it is B. So I'm just multiplying A and B and replace A by the permutation and also B. Like that. Now I use the property that we have here. So I'm going to replace the first element here by BG1, BG2, BGN, ABG1, ABG2, ABGN, and then times this one. And let me write that quickly. Okay, so now when we multiply two permutations, we just make sure that the first row is equal to the row at the bottom here. So that gives me then G1, G2, Gn, AB, G1, AB, G2, AB, Gn. Yes, because this permutation means G1 goes to BG1, and then BG1 goes to ABG1. Well, that's the same as saying that G1 goes to ABG1, yes, and so on. So we just have to make sure that this line here is the same as this line here. When we multiply two permutations. So now we look at this result here. Well, AB is equal to C. So then this is just equal to G1, G2, Gn, and this is C. G1, C, G2, Cgn, like that. So that this is what we mean by C. So we see that this permutations indeed form a group. Yes, this is a subgroup of the permutation groups. I mean, in general, you will have n factorial elements for Sn. The elements in the multiplication tables, of course, only n. So the number of elements is usually less than the number of elements in the permutation groups. So this is a subgroup of the permutation group Sn. Yes. This is Cayley's theorem. It shows that any finite group is a subgroup of the is not subgroup, but it's isomorphic to the subgroup of the permutation group. Okay, time here. Just the next one is a little bit more tricky. I think I need a bit more time for the next one. So we can do it perhaps next time then. It's a good time to stop here then. So is there any question? So tomorrow we have exercise classes. So I think group 3 and 4 should try to prepare for the solutions, and of course if you get stuck, we will do this together like we did before last week. So there is no big pressure on you to solve the problems. Just try them, see if you can do this. I think the fourth problem or the third problem is a little bit lengthy. So the first two I think should be quite straightforward, but the last one or the third one or the fourth one I don't remember, but it's a bit long. Okay, so if there are no questions, then we see tomorrow in the exercise class. Okay, so we say goodbye then.